Climate change is making things less predictable. It's changing seasonality, the normal cycle that you would expect things to happen in, like whether that's when your snows arrive, whether that's when the vegetation typically grows. All of those things are shifting as a result of changes to the climate, and that seasonality can be really key when we're talking about the occurrence of fires.
Hello and welcome to Beyond the Ice, the podcast where we unpack the latest news in climate science with experts at British Antarctic Survey. This time, we're talking about the climate story behind the devastating wildfires which are still burning through significant areas of the city of Los Angeles, California. In this episode, we're going to be talking about the factors that seem to be driving this disaster and how they're linked to wider climate change trends. Later on in the episode, we'll also take a big jump back in history to talk about evidence that's been found in ice cores about the scale of wildfires in previous periods of Earth's history. To discuss all this, I'm joined by climate scientist Ella Gilbert and ice core scientist Thomas Bauska. Thanks for coming on the podcast.
Thanks for having us.
Yeah, thank you.
So before we dig into the science of what's happening here, I just want to acknowledge that this is an unprecedented situation that is still unfolding. We're recording this on Monday, the 13th of January, which at this time there's been 12,000 buildings and about 40,000 acres of Los Angeles County affected by fire. And the weather forecast for the next week suggests that this is going to be a continuing difficult situation. And it's a scary period for the people who are affected, particularly for the firefighting teams who are on the ground in LA who are doing heroic work. So before we talk about the science, Thomas, you mentioned before we started that you do have some experience of fighting wildfires. Can you tell us a bit more about that?
Yeah, that's true. So when I graduated high school, first job I got was as a wildland firefighter with the Oregon Department of Forestry.
Wow,
which is the state I grew up in. So I spent a couple summers out in the forest of Oregon fighting fire on a little tiny, what we call an engine crew. So it's like, think of a big Ford truck, 200-gallon water tank on the back. Yeah, it's probably, I still think it's probably some of the longest, hardest days I've ever worked. Even compared to all the work in Antarctica, we do 18-hour days.
Yeah, you really went for a turnaround there, going from the fire to the ice, didn't you?
Yeah. What
are the main strategies for fighting a wildfire that you use that might read across to the LA strategies?
Oh, that's a good question. It's always a danger. One option obviously is to fight fire with fire, so you have to, one of the strategies is always to remove the fuel, remove the things that can burn to stop the fire. So one thing we used to do was actually to start fires where the fire was progressing. So essentially you have a big fire break, but that's a very, this is harkening back 20 years when I was a firefighter, but this is a very difficult thing to do in a built-up area like Los Angeles, where I work with sort of mostly the wild forest, where you could afford potentially to light a backfire.
Is that kind of scary to see a fire of that scale up close?
No, it's quite tragic. Some of the fires I worked, there were houses burned, and it is quite shocking to see the devastation that it impacts people. So
yeah, thank you for talking about that. So, Ella, I'm going to turn to you. Can we start unpacking what we know about the factors that led to this fire in LA? It seems to be a combination of a real lack of rain in the very near term, and then these very strong mountain winds. So could you paint a picture of the conditions leading up to this January?
Yeah, so this particular event is especially strong, as we know, as we've already sort of heard. And the kind of hellish scenes that are being painted are this perfect storm of a background, large-scale, big picture of climate change, as well as the very much more near-term sort of weather situation. And what we had for the last few years, so 2022, 2023, was actually reasonably wet conditions. And there was a lot of rain and a lot of growth of vegetation. So we had the shrubs, trees, brush, basically. And it just means that there's a lot of fuel available to burn. So like Tom was talking about the controlled burning to remove the fuel, this has just added lots of fuel in the region. Then in 2024, we've had a very dry period. And I think at the moment, or recently at least, there was about 3/5 of California was abnormally dry. And that means that all of that vegetation dried out. So there's lots of fuel that's very flammable in the region around LA. Then most recently, we've had these very strong Santa Ana winds, and these are mountain winds that are formed when air gets forced over steep terrain like we have surrounding LA. And as it descends on the other side of the mountains, it warms up, it dries, and it basically reduces the humidity around LA. I think the humidity was something like 5 or 10%, which is really, really dry. And these Santa Ana winds are actually something we see in Antarctica as well. I actually study them in Antarctica, but we'd call them föhn winds instead, probably in Antarctica, or at least I do. So it's this combination of having a lot of fuel available and these really warm, dry winds, which are really speedy. So once that spark was set and the fire had started, those winds were blowing those embers and the stuff that was burning much further. So the fires spread really quickly. So the winds were, 60, 70, 80 miles per hour in some places. And that meant they were tearing through all of this brush and unfortunately through lots of the actual city and causing these really horrendous scenes that we've been seeing all week in the news.
Yeah, the biggest thing you worry about as a firefighter is the winds.
The chief of the Pasadena Fire Department has said that part of the issue is just the winds are blowing embers miles ahead of the front of the fire that they are fighting. So it's that everything is ready to go up because of that level of dryness and humidity. And then the wind is really kind of exacerbating the speed with which this is travelling and the area over which it's travelling as well. Mm-hmm. Is there anything more that we can say about, did you say föhn winds?
Föhn, yeah. So if you want to pronounce it properly, which is the German word, which is like Föhn over the umlaut. The name in German literally means hairdryer. So it's warm, dry winds that are formed when air gets forced over mountains. We see they're the same. They're called different things in different parts of the world. Naturally, different mountain regions have different names for them. So you might hear them called Chinook, you might hear them called Santa Ana, you might hear them called the Zonda, you might hear them called Föhn. Basically, they're the same thing. It's wherever you have air interacting with really steep terrain, it causes all of the moisture to rain out or become clouds on one side of the mountain, so that when it travels to the other side, it's much drier. And then this dry air gets squished down because the atmosphere is denser at the bottom. So it compresses all of that, kind of like if you're pumping up a bike tire. If you're releasing the air, it gets colder. But if you're pumping it up, it gets hotter. That's basically what's happening. The atmosphere is pumping up the tire and making the air warmer. So you get this warm, dry wind on the other side.
Can I ask a question? It's not the same as a katabatic wind?
No. So a katabatic is more to do with air sinking. Related, of course, because katabatic winds also require a difference in terrain. But when you have katabatic winds, typically in Antarctica, you have this cold air that's really dense and cold sinking down the edges of the continent because it's basically falling downhill. And then they're really cold and really fast. Whereas föhn winds are warmed up and also really fast.
Great. So that's really specific to California and the terrain of the thing. So it's really coming down towards the coast. It's moving through kind of fairly desert-based region over mountains. So it's warm, it's dry. You've got the mountain effect, and then you've got the dropping off into the sea.
Like Ella said, they're all around the world too. So like in Oregon, where I was fighting fire, we call them the Chinook winds.
These conditions are really extreme. So it feels that we're seeing a trend both to increased extremity and then more regular extremity.
Yeah, one of the primary effects of climate change is that it extremifies those extremes. It makes them happen more frequently, makes them happen with greater intensity, and sometimes it makes them happen for much longer periods. So we have more water available for extreme rainfall. Conversely, we also have more drier drought conditions. So if rainfall is shifting, so you get much more water in one place, probably means you're getting much less in another. And we see these different patterns of change in different parts of the world. So it just so happens that this particular part of the world may be experiencing a drying at the moment, but somewhere else might be getting wetter. And climate change kind of turbocharges these extremes regardless of what they are. It could be wet extremes, it could be dry extremes, it could be hot extremes. All of them are being changed by climate change. And in the case of wildfires, it's also sort of related to lots of those different extremes, right? It's about the drought, it's about the heat, because you need the fire triangle, if you like. You need a certain number of things to actually trigger those fires and to help them to spread. So if you're adding heat to the system and you're also drying it out, you're much more likely to get these sorts of wildfire extremes happening when you do get a spark.
Yeah, and I guess on top of that, you've got the wider time period in which these extremes might happen as well. So where there might be a kind of expected wildfire season for California, this seems to be really starting to extend out of those expected months.
Yeah, and this is not the usual season we'd expect to see really intense wildfires. Typically, you get really intense ones in the summer, so that's not what we're having here, of course. It's now January, and typically we see these Santa Ana driven winds in this season, either autumn or winter in California, which is a different sort of wildfire. The property of that wildfire is a bit different to the ones you would see in the summer, which are typically more about the heat and the dryness. And this is much more related directly to that weather.
Yeah, you don't necessarily need a hot temperature for something to burn, right? So one of the biggest worries working in Antarctica is fire, because it's one of the driest continents. Okay. You have a wood source. You have no water to put it out.
It's all frozen
ice, yeah. It's one of the biggest worries working in Antarctica is a nice dry fire. So it's kind of interesting too about another nice example of a fire that just sort of came out of season. In the middle of the winter was those fires in Boulder, Colorado. I think the Marshall Fire. Similar sort of setup. As far as I understand, you had a wet spring, lots of growth. Things stayed dry all summer. The snow didn't arrive in the winter. This is the Colorado Rockies we're talking about. Yeah. Then you had this fire flare up in the middle of December.
I think it's this idea that climate change is making things less predictable. It's changing seasonality, the normal cycle that you would expect things to happen in, like whether that's when your snows arrive, whether that's when the vegetation typically grows. All of those things are shifting as a result of changes to the climate. And that seasonality can be really key when we're talking about the occurrence of fires.
All of this raises questions about our state of readiness for these more extreme global conditions. Last week, there were periods where the firefighting infrastructure in LA was reportedly not really ready for something of this magnitude. So officials have said the hillside tanks that are used to store water for firefighting in the hills were filled to capacity, but then the fire hydrants ran dry. That infrastructure is designed for fires reaching dozens of homes, not hundreds, and the high winds themselves were making it unsafe for tactics like using aerial drops of water. So the things that were making the fire move faster were also things that made other techniques unsuitable. So the fact is that older city infrastructure isn't ready. Do you think this reflects our general state of readiness for the events that we might now be seeing?
I would say that we have created systems to deal with the kinds of extremes that were, what's a typical extreme, but that were extreme in an unchanged climate. We've become accustomed to a certain quote unquote normal and a certain degree of deviation from that normal, which would be a 1 in 100 year event or something. But because of how we're changing the climate, those extremes are getting more extreme and we're just not ready for them. It's happening so fast that it's really hard to keep up and requires so many resources to adapt to the changes that we're seeing that it's really difficult. It's happening on so many fronts as well. It's not just wildfires we're talking about. It's happening across the environment. It's happening across societies. And there are so many different, it's like whack-a-mole, and there are just many, many, many moles popping up everywhere. And it's really difficult to keep track, and it requires a lot of resources to adapt to all of these different changes that we're seeing.
Yeah, so I guess the takeaway for that is just in order to adapt to this rapidly changing world, we really need leaders to be thinking realistically and ambitiously about what looking after human communities and wild places might look like in a rapidly changing world, and kind of addressing that in a really realistic way. So let's go back in time now. Thomas, I'm not sure you expected it to have links to major world events quite so quickly, but you're the co-author of a paper that was released in the journal Nature. Is that right?
That's correct, yeah.
You're the co-author of a paper that was released in the journal Nature at the start of January about the evidence of wildfires in previous periods of the Earth's geological history. So just to go back to basics here, what is an ice core record when we talk about that? Where are you finding the ice and what are you looking for?
Yeah, so ice cores are cylinders of ice. that we drill down deep into the ice sheet of Antarctica or Greenland or other polar regions. They sometimes extend down kilometers deep, maybe 2 miles. That's why we call them the 2-mile time machine. And this particular study was looking at evidence for potential impacts of wildfire on changes in greenhouse gases in the past using the waste divide ice core. And we're talking about a long, long time ago. We have to set ourselves back into the last ice age, or what we call the glacial period. So try to cast your mind back.
How long broadly would you say that is?
We're talking mostly about time periods that are between 60,000 and 20,000 years ago. So the Earth was very different than today. Probably globally, temperatures were cooler, maybe 6 degrees Celsius, and we had massive ice sheets sitting over places like Canada, right? Or in most of the UK. We would have had an ice sheet sitting on the doorstep of like New York City and Chicago, or like here in North Norfolk.
Yeah.
So the climate was very different. It was also quite variable. So we talked a bit about extremes here. What Ella was talking about was sort of extremes, year to year, season to season, maybe on decades. In the past, we had some evidence that the Earth's climate could kind of reorganize itself really quickly within a few decades.
Yeah.
And what we looked for was that we had seen in the ice core record previously that there were these little like bumps and wiggles in terms of CO2 and methane. And I personally find them really fascinating. It's been since doing my PhD in ice cores, it's kind of been one of my goals to try to figure out what's the fastest, biggest change we can ever have naturally for carbon dioxide. It turns out the fastest change we've ever seen for CO2 happens within about a century, and it's a rise about 15 parts per million.
Okay.
So for paleoclimate, that's really fascinating. Wow, how can CO2 change so fast? But actually, it's not all that fast if you compare it to today. A bump in CO2 of 10 to 15 parts per million in a century. We do that kind of rate now every few years, essentially.
Okay. So this is all really in comparison. This is kind of what you would call, quote unquote, natural.
Natural variability.
Yeah, exactly.
So the rate is probably 10 times slower than we see today. Also the magnitude, we're talking about 10 to 15 parts per million. We've shot up CO2 since the 1700s of about 140 ppm. So again, it's 10 times slower, 10 times lower magnitude, but still really interesting. What caused this little bump in CO2 and methane at the same time? And methane was the key, actually.
Okay, cool. And so you've concluded that it was wildfires, that these were the markers of wildfires.
Yeah, so the lead author, Ben Riddle-Young of Oregon State University, he measured the isotopes of methane. And isotopes are great sort of little fingerprints of where these gases came from. And the isotopes of methane are particularly sensitive to what we call biomass burning, essentially, at the time, wildfire. And he saw that most of the methane bump could be explained by a burst of wildfire, again, over maybe about a century or so. And then kind of my role was to do some calculations and figure out, so what's the impact on carbon dioxide too? Because most of the gases released from a wildfire are carbon dioxide, things like carbon monoxide, which we also study, and a little bit of this methane. So it's interesting that wildfires do release greenhouse gases. They're significantly less than any of the burning of fossil fuel emissions, but they still are important to take into account.
Yeah. Enough to show up on this kind of
enormously
long and fairly stable compared to the present day record.
Yeah, they're enough to show in our natural cycles. To give you some context too, there was a huge outbreak of fires in Canada, I think in 2021. And so people did some calculations, and the amount of emissions of carbon dioxide for that one summer of fires was about equivalent to sort of the annual emissions of a country like, I think, Russia or Japan. So that gives you a sense of how big the wildfires can be. The thing with wildfires, though, is they'll burn 1 year, and then a lot of the carbon will eventually regrow. Whereas with obviously anthropogenic emissions, again, it's every year we're pumping it out again and again.
I guess in the current context, the connection that we can make here is our rapidly changing climate is causing more extreme events, and extreme events can look like a wildfire. So all the while we're working to try and reduce emissions produced by humans, we're already in this phase of change where there may be more events like this that are significant in terms of the emissions record now.
Yeah, again, I think they'll the terms of the greenhouse gas emissions from wildfires themselves, it's sort of diddly squat compared to fossil fuel burning, but it just shows that there are processes that were kind of we're triggering now in the natural cycle of things that do exacerbate climate change.
And in terms of looking ahead, does this raise any questions for us in terms of how we are modelling and predicting for a warmer world?
One thing I know is that wildfire is very difficult to model in climate models, in carbon cycle models. It's very difficult to account for. And I just think the main thing, sometimes our evidence from the ice core record presents itself and people will look at it and say, oh, interesting, this is a process that maybe we didn't realize was important before. Let's try to understand it. Let's try to dive a bit deeper.
It is really difficult to model fires, especially when we're talking over many decades or we're talking over large spatial scales as well. One of the things that the project I work on is also looking at is the risk of wildfires in the Arctic, especially as the permafrost changes and as the terrestrial land-based environment changes and shifts in response to climate change in the Arctic. What is the risk going to be? And it requires really state-of-the-art modelling, which is currently what we're working on. And even then, it's still very, very difficult to predict. But it's also difficult to predict in the present climate. So it's this perfect confluence of so many different factors. It's environmental, it's climate, it's weather, it's also land use, it's the human interaction with the landscape. There are so many things going on, and some of it's politics, some of it's economic, some of it's human action, some of it's environmental, some of it's climate, some of it's weather. There are so many things going on that it makes it a really challenging question to answer.
And can you make an educated guess as to what was happening when there were these ancient wildfires?
I mean, I tried to set the stage a bit about being in, the last ice age, essentially. But then we'd have to start talking about like abrupt climate variability and the fact that what you could have had was, eventually go through a scenario where you start off with these massive armadas of icebergs leaving the North Atlantic. A bunch of fresh water gets dumped into the ocean. It shuts off ocean circulation. The northern hemisphere cools a lot. The southern hemisphere warms, right? Have this sort of asymmetric pattern, kind of like an extreme, scenario. And the what's called the rainfall belts or the tropics, what we call the intertropical convergence zone, shifts south to an extreme that we don't see today, and it's pretty extreme even for the glacial. So actually, again, talking about wetter versus drier, the southern hemisphere probably got wetter at this time. The northern hemisphere, where most of the land was, got much drier. And that's potentially what led to these enhanced period of wildfires. So essentially, your main northern hemisphere landmass dried out and fire was enhanced.
Yeah. So these kind of little bumps in the climate record might be almost like portraits of periods in which Earth systems were changing. It might be a signal of that kind of changing climate.
Yeah, we were having a reorganization of climate at the time. Probably not exactly like what we'll see in the future, but that's always the the difficulty.
Yeah, well, we're not there yet. That's the puzzle of this kind of science, isn't it? Trying to find clues to the future by looking at the past and trying to equip all of us.
The problem actually with linking is that what we're having now is like, the Arctic is warming a lot, right? Sea ice is declining. These particular events we're seeing were the opposite signal of what we're seeing today. And it's not the same forcing either, right? Because, like I said, little bumps of CO2 at the time were quite small. What's driving climate change today is greenhouse gases.
Yeah.
What was driving climate change in our ice core record was sort of big fluctuations in ocean circulation. So,
cool.
Just caveat.
Thanks for explaining that.
Classic scientist.
I hope you enjoyed this episode of Beyond the Ice, and if you did, we'd love you to leave us a rating or review on the podcast platform that you're listening from. It will help other people find the podcast, as will sharing it with friends, family, and colleagues. See you next time.